So my name is Colleen Bertoni. I'm a computational scientist in the performance engineering group at Argonne. I'll be talking about OpenMP on Aurora for the first 30 minutes, and then Yelo, who's also a computational scientist at Argonne National Lab, will do about 30 more minutes. And we're mostly talking about OpenMP on Aurora, but OpenMP, the same stuff is equivalent on Polaris, and in the demos we show or we have instructions for both Polaris and Aurora. So just, yeah, the agenda, 10 minutes of slides and talking about like why OpenMP. I know a lot of people, OpenMP has been around a long time, so a lot of people have experience already with definitely at least the CPU side of OpenMP. So it'll be pretty short. And then some background on topics for using GPUs with OpenMP Offload. Then I'll do about 20 minutes of 101 style OpenMP demos, kind of similar to what Abby showed, with like simple examples. I'll do this on another Intel GPU system, so slightly different than Aurora, but still using the same type of GPUs, and so the compile flags and compilers will be the same. And then we'll switch over to Yelo to talk about efficient OpenMP code patterns and some advanced usage, and then we have some time for Q&As. So let's get started. So first, why OpenMP? So OpenMP is an open standard, which means it's a set of environment variables and APIs that are supported pretty broadly across vendors. It's mostly focused on parallel programming. It can run on different types of systems like CPU threads, GPUs, and specialized for SIMD units. One important part about OpenMP is that it has support for C++ and Fortran, so it's one of the few that will still support directly Fortran. Currently, it's supported by a lot of vendors, but for people interested in at least the DOE HPC space, Intel, Cray, GNU, and LLVM compilers all support OpenMP for CPU and GPU. It's supported on Aurora, Frontier, Perlmutter, and other big systems that possibly a lot of you have already run on. The standard document itself is huge. It's very large, and the reason is because it has lots of support for lots of different types of parallelism, so fork and join, SIMD parallelism, device offload parallelism, tasking parallelism. So for this, we'll mostly be focusing on device offload parallelism because, as you saw earlier today with Victor and Chris, the main area where you have high memory bandwidth and a lot of computing power is on the GPU. So if you're running on Aurora or Polaris, you really want to run on the GPUs. And then one question is like, why would you want to use OpenMP instead of a C++ framework like Cocos or SYCL or CUDA? So one thing is that it's very easy to get started. It's completely trivial to parallelize loops. So if you've done CPU OpenMP, all you have to do is add a pragma around a loop and it's parallelized, and then similar for GPUs, you need to add just a pragma, and then you'll offload to the GPUs. Of course, extra stuff with optimization, but at least incredibly easy to get started. It also has some convenience clauses like the reduction clause, which can really simplify some things like data reduction. So with that, I'll talk a little about just using GPUs with OpenMP Offload. So starting back with CPU opening parallelism. Again, I know most people are familiar with this, but just as the reminder for this step and then comparing this to what the GPUs look like. So for OpenMP's CPU parallelism, usually to do that, you would take your code, find loops you wanted to parallelize because they had a lot of work, and add a pragma OMP parallel 4 around it, where the parallel is what's going to spawn the threads to run on the different cores on your CPU. And then the 4 is what cuts up the loop and sends different iterations to the threads and the thread team, ideally running across the different cores. So for GPU, again, like I said, the nice thing is that if you've already parallelized, if you've already identified what loops you want to offload, or what loops are computationally heavy, so you probably want to offload it. This is really easy. You just take the pragma OMP parallel 4 and switch it out with a pragma OMP target teams distribute parallel 4. So you can see that the pragma's directives are slightly different. And to go through why they're different, I'll go in a little bit more detail about each of them. But high level is that the target teams is similar to just the target teams parallel is similar to just parallel, and distribute for is similar to just the for in terms of creation of threads and distribution. But we'll go through this in detail just to get, I think it's important to understand what the directives are, at least at a high level. So just looking at the picture on the right, so to look at this, we'll just assume you have a system that has one CPU and it has one GPU. And inside of the GPU, there are different subcomponents of the GPU. So here, three. These are like subcomponents like the SMs or the XE core, the SMs on NVIDIA or the XE cores on Intel GPUs, where you have special things inside of the subcomponent, like access to shared memory that's only shared inside of the component, or special synchronization hardware. So the target construct, the Pragma OMP target, this is the thing that just says stop running on the CPU, because you always start running on the CPU, and transfer execution control to the GPU. So target construct just says stop CPU, go to the GPU. There is some default data transfer with this, but we'll leave it aside for the second. However, this does run in serial on the device, so it's good for sometimes if you want to do debugging, because you only run one thread on the device, but overall it's not what we want, because we know that we have a lot of computing components on the GPU, so we want to take advantage of them. So that's where the teams construct comes in. This creates a league of teams, each still with only one thread, but still at least multiple running in parallel. These run concurrently on the SMs, on the subcomponents first, or so SMs for NVIDIA, XE cores for Intel. But of course, they're not using all of the components or the execution units yet. So the parallel contract is what creates multiple threads in the teams. And the thing about teams is that they run on the subcomponents, again, because of the specialization of the hardware. Like inside of a team, or inside of a SM, you have access usually to faster memory, like the shared local memory or special synchronization hardware. So with the target teams parallel, we're running on the device with a lot of threads. And then back to this picture. So once the target teams parallel have launched the threads, then the distribute and the for are just what distribute the iterations of the threads. So that's just the high level how you express parallelism and how you change execution control to the device. But then, of course, the other big one is transferring data, because if we don't have data on the device, we can't use all of the computing power. So the way to do that with OpenMP is typically the map clause. There are some default data transfer that happens, but just to keep things straight, generally we recommend using the map clause or using an unstructured way of transferring data, just so that you are clear about what's happening. And we'll show some of this in the demos too. So for here, you have the host CPU and the device, and you do map to from array A and array B. So this just says send the arrays A and B to the device, and then when you get to the end of the offload region, send them back from the device to the host. And if they're in the map clause, that means they're shared and accessible by all of the threads on the GPU. That's different from things like we can see the scalars like num and scalar, which we don't specify with the map clause, but by default, those are transferred as first private, so private per thread versus the map clause, which is shared. And of course, you can change the defaults or change specifically for different scalars or other variables. Okay, so it's a short just overview, and we'll see way more detail or at least go through it again in the demo, but just the quick, if you're running on Aurora, what the compilers and flags are. So again, it's Fortran C, C++, kind of the standard MPitch compiler wrappers, MPI4, MPICC, MPICXX, and under the hood, the Intel compilers, IFX, ICX, and ICPX. They all, if you want to turn on just support for CPU threads, they all have the same flag, so that's at least kind of nice. So FI OpenMP, and then if you want to target the GPU devices, meaning that the Pragma OMP target clause will be honored, you need to do F OpenMP targets equals spear V or spear 64. Chris had touched on this earlier for JIT compilation versus AOT compilation. So the shorter one, this if OpenMP targets SPEAR64, that does JIT compilation by default. But if you want to use AOT compilation, use that SPEAR64_gen and then -XS device PVC for ahead of time compilation. And this is all at this the documentation link. So feel free, you don't have to memorize this, you can go look at the documentation link. And these are the compilers that are on by default on Aurora, so you would see them by default. Just before going to the demo, just kind of some good news from a recent paper we did at the IWAMP conference. So this was taking two conformance benchmarks, OVO and OpenMP validation and verification, and running them on the two big systems that we've been talking about today, so Aurora and Polaris. So these are conformance benchmarks, so they're not doing anything with performance. They're really just looking at, with the set of directives that is correct, does the compiler compile correctly and give the correct result? So some of them use really uncommon OpenMP directives that usually applications don't have. So some of these rates are a little bit lower, but overall, what we can see is the pass rates are pretty high across the board for C++, Fortran, and Intel and NVIDIA. And then also that the Intel ones are often slightly higher than the NVIDIA ones, meaning that if you're coming to Aurora with OpenMP Offload code that was running on NVIDIA GPUs, and there's a high chance it will run fine on the Intel GPUs. And of course, if it doesn't, please report the bugs. We really like dealing with bugs and getting things working. So this is just good news that generally things are working pretty well. Okay, so now I will switch to the 101 demo. If you are already an OpenMP offload expert, you can go think about something else. So this is really for getting started. So you can follow along at the GitHub for the workshop, and then in programming models, OpenMP and demo. I'm gonna stop sharing this screen and switch to just sharing my desktop. Okay, share, and I just share my desktop. Hopefully that'll work okay. Okay, can I move this? Can you guys see everything okay? Can you hear me okay?
I can see, but I am wondering if you can slightly increase the font size or just the page.
Yeah, I can definitely do that. Is that better?
Yeah, is everyone else is happy because I can see it fine. Yeah, I think it looks good. Thank you.
Okay, I'll make a couple bigger later. So I've already git cloned the repo and gone into programming models OpenMP demo. And inside there's a README, which I have open on the right side. And we'll just go through this. This goes through kind of the three things I talked about. So the concepts, just offloading code to the device and getting device info, how to express parallelism and mapping data, and also doing sanity checking for all of these to make sure that they're acting as expected. So README is on the right, and then I'll be executing things on the left side and showing some code. So there's C++ and Fortran versions. I'll show both of the code for both of them. They're very similar. But I'll only execute the C++, but you're welcome to follow along or later go look at the Fortran versions. So the first thing just to show is just talking about changing execution control and getting some idea of the number of devices. So with OpenMP, one thing is that there are a lot of useful API, just runtime routines. So you can use OpenMP to just get the number of devices. So get num devices in Fortran, get num devices in C++. So Fortran's on the right, C++ is on the left. So basically the same type of call. OpenMP target, this is the directive that just says, so the CPU is running along, it prints this. Once a thread on the CPU hits this, it stops at the moment. There are ways to make it asynchronous, but for the basic, the CPU thread stops, execution control transfers to the GPU, And inside of the GPU region, it first says if OMP is the initial device and then a not. So if you're not the initial device, again, this is an OpenMP runtime call. The initial device is the CPU because we started running there. So if you're not the open initial device, then print hello world from the accelerator. Otherwise, hello world from the host. And then at the end of the curly braces for C++, or at the end of the pragma OMP target, or pragma OMP end target, the target region ends and execution control goes back to the CPU, and then it goes along. So this is just the high level basic, can we run on the device? So for running this, so the instructions are on the README. So first, setting the environment properly. There's a way to set it for either Aurora or Polaris. This exact same source code works anywhere. The environment I'm in is the same as Aurora. So we'll skip, and my environment is set up correctly, so let's switch past that. So first, offloading code to device. I'm just gonna copy paste. It's just make O1 target construct. So we compiled, like we noted, like I mentioned before, it's ICPX is the C++ compiler, and then -fi OpenMP and -f OpenMP target sphere 64, and then just the name of the C++ file and the output, or the name of the executable. So let's run this O1 target construct. Okay, so we see it prints there's 7 devices and hello world from the accelerator. So good that we see hello world from the accelerator, and we see that we have 7 devices. But of course, we should do some sanity checking to see, is OpenMP telling us the right thing? So you saw, I think Abby and maybe someone else had mentioned you can use cycleLS to get an idea of what devices there are. So I did cycleLS, and I see indeed there are 0 to 6, so 7 GPU devices. These are the Intel PVC. So if you do this on Aurora, you'll see it come up as the Intel Data Center GPU Max 1550. So that's good. Then the other really important part of sanity checking is, again, yes, it printed hello world from the accelerator, but can we, again, verify, because we want to be 100% sure we're actually running on the device. So there are some profilers you can run, and I know J-Hook and Thomas will talk about profilers later. I'm going to give you a little head start just because it's really useful for sanity checking things. So you can run iProf just around the executable. Let me make this bigger. And again, it just executes, it prints the output from before. This is really similar to like MVProf or other command line profiler, but RockProf and other command line profilers. So hopefully you have some sense of what it is, but just runs the output, then it prints a lot of stuff. Some of it for now you don't have to think about. So just runtime calls, what's happening in the level 0 backend. The thing I want to point out is the device profiling section. This inside of it tells you what is running on the device. So here we see this, which says a function name and a line number. So this is the function you're in and the line number, and that's what is being offloaded with OpenMP Offload to the device. And when we look back at the C++ code, that is in function main, and it's on line 8. So it's just telling you OpenMP Offload region in function main line 8 was offloaded. So that's just our double checking things are being offloaded as we expect. Okay, so the next thing, so now, yeah, we checked that we can run the device. Okay, that's good. So the next thing was expressing parallelism. So let's move to the next example, O2 target teams parallel for Fortran and C++. So for right side's Fortran, left side C++. So here, like we talked about, it's pragma OMP target teams distributed parallel 4. For now, I'm just gonna remove this to make it more interesting. So this is, we know we'll switch to the device, and then the teams distribute parallel 4 should take this loop, split it up between a bunch of teams and threads, and all it does inside of it is print for that index I, I'll make this bigger, for that index I, which thread am I, out of how many threads on all the teams and out of how many teams. So it's just to check how many teams we have and how many threads per team. Fortran is the same, except target team distribute parallel do, just printing the same API calls. So switching back, I'll just copy paste from here. So make O2 target teams parallel. And again, it's just ICPX with compile flags and the name of the file. And then if I run this, O2 target teams parallel. Okay, so it's a huge amount of output because there were 10,000 iterations. What we see, there are 16 threads per team and 632 teams. And indeed, they are being split up by index, so that's good. Maybe the question is, why are there this number of threads and teams? So OpenMP always uses a heuristic for the number of threads per team and the number of teams. It does its best to guess based off of like the iterations of your loop and things like that, what the right number is, but it is something you can optimize yourself if you want. So you can do this for num teams. So just to make it simple, 2, so that's 2 teams, and thread limit 2, so 2 teams with 2 threads each. And then just to make it easy to read, we can set that to 4. And then we can recompile, make O2, and then rerun O2, target teams parallel. And then we see the four indexes, and we see that there are 2 threads and 2 teams. Okay, so we looked at changing execution control to the device, and then how double checking that we're expressing parallelism and is actually getting cut up into threads and teams. So the last thing, and one of the really important ones, is mapping data. So that's the third example, and O3 map, and O3 map. So here, this is just doing implementation of DAXB on the GPU. So it's taking in both, C++ and Fortran, we allocate 2 arrays, A and B, of size 1024. So A, B of size 1024, just initialize them to something on the host. Then we have the pragma OMP target teams distribute parallel do again. So we want to run the computation on the device, and all we're doing is taking a scalar, multiplying it by each element in array B, adding it to A, and then we're done. That's a DAXB. And then we end the target teams, and then we check that A had the value that we were expecting, because that's what we were computing on. And to do that, we need to do data transfer correctly. So here we're taking array A and mapping it to the device so that we can use it to compute on, and then because we get it back at the end. And then we're mapping array B just to the device because we don't care what it is at the end. At the end, all we care about in this little code is A. Then we, of course, check the answer, success or fail. So high level, just kind of showing the data transfer. So let's compile this. It's just make O3 map. I misspelled that. O3 map. And then we run it, O3 map. So great, it worked and gave the right answer. But of course, again, at least when you're starting out, especially sanity checking to be sure what's happening is what you think is happening is really important. So again, let's check that the data transfer we thought was happening was actually happening. So we can use iprof. So iprof O3 map. So print success, that's good. Then the other thing we now see, so again, the device profiling section tells us that line 27 in the main function is what was offloaded. And indeed, this is line 27. So that's good. Then there's an explicit memory traffic region. So what we can look at here is the transfer to device and the transfer from device. And in transfer to device, what we see is there are 2 calls, and then average, min, and max are all basically 8 kilobytes. So they're all the same. So 2 calls, each of 8 kilobytes. And if we look at the code, what we see is we're sending A and B, which are both size 1024 double precision. So that's 8 times 1024. So that's 8 kilobytes to the device. So A and B both sent to the device. And then for transfer from the device, so that's back, we see only a single call. So that's the A being mapped from the device. So good, things are as we expect, 2 to the device and 1 back. Okay, so far so good. Then we want to look at slightly more complicated example just to show that we can do that. So 03, so let's say we want to use this offload region, but we want to call it multiple times. So like good programmers, we put it in a function. Now it would just call DAXB. And now we allocate 3 arrays, A, B, and C, initialize them on the host. And now we want to call DAXB on A and B like we did before, but then we want to use the output A and add it times another times the same scalar to array C, and then check that the answer is right. So same thing in Fortran, we're just pulled the same offload region from the other example here, and we want to call it twice on two different arrays. So let's check that that's working as we expect. So make O3 map function. And then we can run it. 3 map function. Again, success, that's good. And let's use iProf to just double check things are working as we expect. So success, that's good. Then again, we look at we check, yes, we offloaded. Now it's function named DAXB at line 10. And we check our data transfer. So to the device, we had 4 calls of 8 kilobytes, and from the device, 2 calls of 8 kilobytes. So we can see if that makes sense. So for each call to DAXB, we were doing 2 transfers to the device. So A to the device, B to the device, and then B, or the A just back from the device. So 2 transfers, 2 and 1 back. And then we call DAXB again with C and A again. So C and A are both sent to the device, and then C is sent back from the device at the end. So that makes sense. That's a total of 4 to the device and 4 to the device and 2 back from the device. However, when we look at this, what we can notice is that we're sending, in this first one, we send A to the device and from the device, and then in this second call, we then send A back to the device and back to the device again. So there's no need to be transferring it back to the device and then to the CPU and then back again, because we already are doing it. So the thing to note here is that with this style of OpenMP programming, the data transfer is tied to the compute. And in this case, we really just want to split the data transfer from the compute so that we just send A, B, and C to the device once and then pull C just back at the end, because there's no need to keep transferring data back and forth. And that's what we can show in our final example, how to do that. That's with unstructured data transfer. And it's really useful to use because the memory bandwidth from a CPU to a GPU is like orders of magnitude slower than the memory bandwidth just touching memory. So you really want to be able to decrease, if you're doing data transfer you want to be able to decrease it. So this is the same as before. We still have the DAXB functions. But the difference is after we've allocated the data and initialized on the device, we're doing pragma OMP target enter data or OMP target enter data here. And we send them to the device up here. Then we do the DAXB calls, and then we just get C back at the end. And we can actually leave the maps here because OpenMP does checking of whether things are on the device or not. And since it will see that they're already on the device, it won't transfer them again. One other thing I wanted to mention for Fortran, probably you've seen that in the C++, we're specifying the length of the array to send. In Fortran, we don't need to because these are allocatable arrays and that stores the size with it. So it's one nice feature of Fortran. Okay, so let's compile this and then check. So make bottom, make O3 map unstructured function. Okay, compiled, and then we can run it, O3 structured function. Success, that's good. Let's run it with iprof, O3 structured function. Success, that's good. We make this bigger. So indeed, we see here for, we see our DAXB routine is called twice, and we see transferring to the device 3 calls, which is the transfer of target enter data ABC, and then from the device 1 call, which is this transfer at the end. So that was one thing to keep in mind is data transfer, and one way if you need to split the compute from the data transfer is with the unstructured functions in OpenMP. And that's all I have. So let me stop sharing, and then we can switch to Yay. Yeah.
Do you see my?
I see it. It says you've started. Oh, yes. Now I see the PowerPoint OpenMP efficient code patterns importing tips.
I need to swap my screen. Give me 1 second. Okay. Okay. So I'm going through the efficient OpenMP code, the code patterns. So, and also give you additional porting tips. In terms of efficiency, I mean here not just code runs fast. Of course, that's a universal, how to say, desired for code, but also means the code needs to be neat and efficient for developers to develop them. So that's why I will cover a bit patterns like how to choose between directives and APIs in OpenMP, and also give you hints how to write performance codes. And also the last part is the above 2 parts are actually applies to both the Polaris machine and Aurora machine. But the last one is specific to the Aurora machine because it's SQL, directly using SQL, and a lot of them are Intel extensions. Okay, so choose between styles. OpenMP programming model itself is portable, but it actually gives you a bit of flexibility to choose what programming style you can use. On the left side, I mean, you can program with purely directive. The example I give you is just to allocate data on the device. This in the directive way, actually, when you're not using OpenMP, you're not compile for OpenMP, it just has 0 impact. This directive line gets ignored. In addition, when you are doing OpenMP, you can easily use the offload target offload disable to kind of fall back on the host for debugging. On the right side, OpenMP actually also gives you a set of APIs you can allocation for data management, device management, that kind of thing. However, these APIs are source code, so you have to protect them with macros if you're not compiling for OpenMP target offload. So it gives you more precise control, but on the downside, you have to do a lot of works in the source code. So it turns out when you're writing a scientific code, the goal is to write something kind of easily readable and as little pollution from the programming model as possible. So in this simple calculation, you want to just fill an array. On the left side is using directive style, and on the right side is using API style. You could see that the API style requires you to put way more lines. So my personal recommendations when you think about how to program in OpenMP, think it in a directive way rather than treat it as an CUDA alternative. You write in a CUDA style, which is actually add you a lot of maintenance burden. So, okay, the second part is making good use of OpenMP. OpenMP can give you very simple code to make things working. However, to improve to have the code kind of performant and can be used to compete with other programming models to convince you that you can write OpenMP with very efficient code, and then due to its portability, you gain the benefit that to achieve that, you have to do a lot of steps and kind of get the OpenMP target offload used correctly. So I would emphasize, as Colleen has shown in her examples, that you have to take care of the data movement. So think about data locality, how to localize your data, reduce movement, make constant data like resident without just copying them every time when you need. So that's the homework you need to do to write the performant OpenMP code. So you have to think about the reason is clear. The CPU GPU interconnect is slow. It's always slow. You should avoid thinking as a slow by a bit. It's a slow by a lot, and even over generations of technology improvement, this bottleneck was always slower compared to all the capabilities improved on the CPU and on the GPU. So by design, your software, if you want it to kind of work for not decade, but at least 1 decade, you have to think about how to handle the data movement correctly. A lot of OpenMP tutorial teaches you how to program kernels, but you actually have to think harder arranging your data movement, because if you mess that up, regardless how you make your kernels fast, you're gonna suffer. The code performance will be very bad. And to design data movement, you have to wholly understand the whole algorithm implementation and bring in your domain expert knowledge. Okay, so just give you this simple code example on the right side. You can simply write 1 line OpenMP and get the for loop running on the GPU. However, if I'm helping you to break it up what it is doing. It's actually first allocate the memory for the array on the device. So allocation means it's a very process. GPU needs to kind of somehow lock up the memory mapping table, and I give you the allocation and release certain constraint. Once you get the device memory, the runtime starts to move your data because your array 100 element needs to be moved from host to the device. And then the GPU, the runtime will launch the kernel for you. And once the kernel computation completes, the data gets transferred back. And also the device array needs to be destroyed. So there are multiple very slow and slow operations. That's why you've seen in Colleen's example that you need to pre-arrange your data allocation and also pre-arrange your data movement if it's possible. So OpenMP gives you those enter data, exit data, allow you to pre-arrange those device resident data. In many calculations in scientific computing, think about like you are doing molecular dynamics or you're doing Monte Carlo. You're just stepping through time. So the middle part of the calculation, it's repetitive. It's the same. That's why a lot of data can be pre-arranged. So think your algorithm in that way and do adjust the data usage and allocation kind of the arrangement to achieve your good performance code. Here I'm explaining you once you pre-arrange the data, but probably you still need to transfer some data during the calculation for the result to be checked out on the whole side to make decisions. That's why you still have data movement. However, OpenMP runtime is helping you try to get your data movement asynchronous. So when we do programming, GPU programming, we think the lessons tell you you need to kind of do asynchronous calculation. But if you're using OpenMP, OpenMP is actually helping you doing it instead of you doing it explicitly. That's one of the advantage of using OpenMP. So in this simple example, OpenMP will move your data, this array, because I said always, that means data will be moved to the GPU and moved back from the GPU at every time this target gets executed. So the OpenMP runtime, when it figures out that, okay, I don't need to do any allocation, I don't need to wait for the allocation, the device space, memory space already available. So the runtime will start kind of scheduling all the transfer and computing using the underlying asynchronous mechanism provided by GPU. So both, if you're using like LVM clam for OpenMP for C++, or you're using all the Intel implementations in the one API for both Fortran and C, they always leverage the asynchronous CUDA stream or level 0 immediate command list to help doing all the calculation asynchronously. So it's kind of gaining you good performance in that way. So here is just a simple figure that if you just write the code in the way I suggested, you do a profile, you will see actually the runtime is doing all the asynchronous data movement and computation. That's why you see that it spends a little time on, there's only one synchronization at the end of this OpenMP target region. So to save you from doing multiple synchronizations. In addition, OpenMP actually, the OpenMP implementation, the runtime implementation also allows you to have multiple threads talking to the GPU. So on the right side, I'm just faking an example. You can have high-level threads, and each thread kind of issue OMP target region. So those computation within each OpenMP target region, it's kind of asynchronous. Then between different target region, you get those overlaps. And if you see the overlaps, you learn that, okay, doing GPU computation, we should try to overlap the computation and data transfer. That's the benefit you receive out of the OpenMP runtime library. Beyond parallel 4, on the host side, like there's also, you can use additional features from OpenMP, like OpenMP tasking. So these tasks will be executed on different threads, and you can schedule different work spawning different offload regions and get the benefit of this. So I'm just here just showing you a confirmation. When you run profiling, you will see, yeah, different streams get different computations being enqueued, and at runtime that the GPU will be kept busy, kind of serving different threads, and you have way less gaps on the compute side and also on the data movement side. So the last thing is, if you need your data movement asynchronous transfer very efficient, you actually to leverage the pin memory. So by doing that, the GPU hardware will be able to use its DMA hardware engine, moving data between the DDR and your device memory without interfering the CPU, without asking CPU for doing extra works. So there are multiple ways, but so to achieve pin memory, actually both CUDA and SQL offer you APIs to kind of pin the memory. So the method one is, if you already have memory allocated, you malloc a memory, and you want to ping that specific memory, you can use a CUDA host register API. And on the SQL side, Intel is providing this experimental API it's called prepare for the device copy. There's a matching one for destroy for the reverse operation. You can check it on the SQL or on the CUDA documentation. The second way is If you don't use malloc, you can directly allocate the pin memory. For CUDA, for Polaris, you can do the CUDA malloc host. And for SQL, it has two versions. Some needs the aligned version. You can use the align alloc host. So by doing that, you can achieve the host memory being pinned. As OpenMP users, currently you can use an OpenMP extension, then it provides you an API to allocate pinned host memory. So it's currently supported by both the upstream LVM, you can use it for Polaris, or it is also supported by WEM API. So you can use this, making sure your host memory is pinned, then the OpenMP asynchronous computation will be automatically doing its best to maximize its transfer rates. Okay, so the last few things. So when we are using OpenMP, however, a lot of vendor libraries are provided using its preferred API. So for CUDA, you get those cuBLAS, those libraries, right? For SQL, for Intel, it provides you the one API libraries, or you may get something from third party. Likely, they are programmed in SQL. Even though OpenMP now actually on the Intel side supports you to call the one API BLAS, one MKL BLAS on the GPU. However, it's only a subset of features being supported. So that's why we want the best of both worlds. We want the vendor preferred ones, and we also want the OpenMP to max out our portability. So that's why I'm here showing you how to kind of use the interoperability feature offered by OpenMP and to link it with the SQL so you can use all features from both sides. So OpenMP, the latest OpenMP, I think it's around 5. It's giving you clear ways. It's called OpenMP get interrupt pointers. You can initialize those interrupt object and then use it on the other programming model. So Intel actually offer you not just this one way. So here I'm using, so here my OpenMP is implemented on top of level 0. So I'm first to query OpenMP runtime, could you give me the level 0 knobs? So I extract those level 0 knobs and then use them to reconstruct SQL objects. So you think about the level 0 is the bottom layer serving both OpenMP and SQL, and I'm just pulling it out of OpenMP and make it talk to the SQL side. If you don't want this complicated way, there's another way you can, instead of preferred type here, I'm using preferred type level 0. You can choose to prefer just SQL. So it will directly give you SQL objects and also helps you to kind of directly use that SQL queues in your other library calls. However, that method somehow, actually both methods, you need to be careful about the lifetime of those objects. It depends on which one, OpenMP or your SQL, which initialize first. So you need to destroy them in the reverse way. Otherwise, you might get like null pointers when you're trying to destroy an object, which probably its parent has been annihilated by the other side of the library. So, but by doing that, using this interrupt thing, you can access the best of both worlds, give you maximum flexibility. So the last thing I want to just quickly go through. So somehow OpenMP has designed a portable layer, so that means it's missing certain specific features provided by vendors. With the interrupt thing, and I kind of enable extra features. I personally find, yeah, we definitely want to care about how much GPU memory being consumed in an application. So the SQL side actually offer you this extension, and you can do it this way. However, when you're using OpenMP, as I mentioned, there's a catch. You have to care about which library started first. So if your app starts the SQL first before OpenMP, you can explicitly initial the level 0 sysman service. Then you can create the GPU memory later. However, in my code, I found that actually my OpenMP runtime library initialized first. So I need to use this environment variable explicitly telling an OpenMP, make sure level 0 is initialized properly with sysman. Then later in the code, I can query the GPU memory. So when you are using both OpenMP and SQL, there are a few extra things you need to take care of. Okay,